Hello and welcome to the webinar. Today we are going to be talking about the process to generate a shock test from field data. And this is specifically regarding using a tool like SRS or user-defined transient and creating a complex shock to replicate a complex shock that would be experienced in the real world. As always, I start with Vibration Research's core values: collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. And this is where I would typically jump into our innovation slide, which talks about the innovations that Vibration Research has implemented in software that really set us apart and drive the industry to be new and improved and always improving testing. But in this case, the tool that we're using is not one of those innovations. One of those innovations are field data replication, the fatigue damage spectrum, Kurtosion, and IDOF, all of which are designed around running a better test, but are not really used for analyzing or quantifying or creating a shock test. Today we are going to be using shock response spectrum and user-defined transient, and the user-defined transient will just be in the background. But we are going to use these to not only analyze field data, but then generate an appropriate shock test based on that real-world environment that we record. So first we want to talk a little bit about SRS. And I'm not going to go into extreme depth on the math and the theory and the background of SRS. We're just going to do a basic introduction and then jump right into the application. So SRS is a tool that we use to analyze complex shock environments. And it can be used to compare different environments. It can be used as an analysis tool. And as we'll see, it can also be used for test generation. So in regards to how this whole calculation works, SRS is not necessarily real. It is how a series of single degree of freedom oscillators would respond to an impulse. So it's essentially assuming that at every point plotted, you have a resonance at that frequency. And it says, let's say, for instance, my first frequency here, F1, is 10 hertz. It is, if I had a 10 hertz resonance with this Q and damping factor, this is the peak amplitude that would be measured at 10 hertz for this impulse waveform. And we just progress through those different frequencies and plot those points on the map or on the graph. So it is how a set of single degree of freedom oscillators, each independent from the other, would respond to an impulse. This was originally developed by Dr. Marcus Biot in 1933. He was investigating how a building would respond to an earthquake. And rather than building a whole bunch of different structures that all have different frequencies and different natural frequencies, different resonances, different characteristics, he just assumed that there was a resonance at every frequency and what that would do to the structure. So this is a tool that was originally used to evaluate the response of a structure to an earthquake. After that, the Navy and the military got a hold of it, and all these other companies started developing complex shock environments and using the SRS to quantify them as well as to compare them one to another. So it is a great tool for that. It's just very important to remember that it is not necessarily a real acceleration, especially at every individual frequency. So as I said, it started out as a seismic earthquake structural type analysis tool. The Navy got a hold of it, and now it's used in a wide variety of industries for looking at how something would respond to a complex shock environment. And these complex shocks occur all of the time and can't be tested through a normal long duration sine or random test because it just doesn't excite the product in the same way. So we need to use some kind of shock test in order to properly evaluate whether or not our product will withstand these sharp transient environments. And if you ever have a chance to look at this video, Up Aerospace SL-10 NASA Flight Opportunities Mission, it's a cool video that shows the stage separation of a rocket and catches it in space. And you can see this really sharp event that occurs. They use either explosive bolts or some other shear mechanism that has a charge associated with it to separate those two stages perfectly and push them apart from each other. Now, if I have electronics that are mounted in and around that range or other components that need to stay operating in and around that event, I need to properly evaluate those products to make sure that they are in fact capable of remaining operating after that transient event has occurred. See if we can go fast forward through this. So here you can see that rotating around, and as it comes into view, you get that perfect separation and you get that shock that is going to transition all the way through that barrel. And we need to make sure that our product can in fact withstand that type of environment. So once we have the SRS, the shock response spectrum, this qualification or this level of maximum acceleration that our product will exceed at these frequencies, we need to then synthesize a pulse, typically, that will exhibit similar frequency response characteristics as the environment that we are analyzing. And there's synthetic pulses that can be used. Linear chirp and exponential chirp are really a sine wave that progresses across a frequency range and it changes frequency either linearly or exponentially. WaveSine is a wavelet analysis tool or a wavelet generation tool where your sine waves in the centered case are all stacked on top of each other, aligned left or alternating, and then sequential rather than putting those sine waves on top of each other where they can complement one another. Actually stretches that waveform out and makes a longer duration but only single frequency at a time. Burst random takes a random waveform generator and outputs a specific burst. You can define some frequency content associated with that. So the key to remember is that when we use these synthetic pulses, all of these synthetic pulses can be used to generate most of them can be generating the exact same SRS response. So it's a very important consideration that needs to be made when selecting the waveform that you are looking for. If like a stage separation event is what I'm trying to replicate, I want to use something that's like WaveSine centered, which is almost like a terminal peak pulse run like a classical terminal peak pulse. It's very short duration, it's a sharp transient, and you can cram a lot of frequency content into a very short period of time. If I'm trying to replicate something more like an earthquake or a launch event as a whole, I might be straying more towards burst random, where that time duration gets stretched out farther and farther, and I'm more similarly synthesizing what that real world environment is. Now, the tool that we are generating or we're using today is not necessarily using a synthetic pulse, and in fact we're not going to use a synthetic pulse. Rather than using one of these synthetic pulses, we're actually going to manipulate the real-time history that we record in order to use that as a base reference for our enveloped profile that we generate. And we'll talk about that as we continue to go. So now we're going to talk about the application. Today I have a Milwaukee drill. It's an impact drill. I have one accelerometer mounted on the frame of the drill right where the battery would mount, and I have another one that is mounted to the back of the battery. And we are going to record that environment. And some important considerations to make when mounting accelerometers and even selecting an accelerometer is to have an understanding of the event that you're trying to acquire. So I want to make sure that I have sensors that are capable of measuring the peak accelerations that I expect to see, and that I have them mounted such that I have the ability to appropriately measure the frequency range that I'm looking for. Most of the time when doing shock type acquisition, the best bet is to stud mount your accelerometers, and if possible use a grease or non-compressible fluid in between the accelerometer and the mating surface in itself. Today I'm really not expecting extreme high frequency ranges, and I know the relative peak accelerations that I'm going to get, so I'm just going to use, I have some 10 millivolt per G triaxes, and I have super glued them to my drill rather than drilling holes into them. So we are going to set our sample rate for 10 times the highest desired frequency. Again, this is for shock analysis. Really you want as much sample rate as possible to prevent any aliasing and or oddities that might occur once you start integrating from acceleration into velocity and displacement for analysis. So the higher frequencies you can get, the better, but in this case we will probably only analyze out to 5 to 10 kilohertz because that's all my shaker would be able to generate if I had a very small component with a high frequency shaker. If you're running bigger components where your shaker has a resonance at 2200 hertz, really I'm not going to be running a test at anything greater than a couple kilohertz. So we have a few methods that we could look at today. The easiest one would be to use one piece of hardware from Vibration Research, either the Observer 1000 or the VR9500, have it connected to a laptop or PC, and utilize the transient capture software in Vibration View. If I use this transient capture software, I could set up my graphs and my analysis so I could, as I acquire these pulses, automatically calculate all of the plots that I want to look at for comparison and analysis and save that as a data file. For the sake of being a little bit more generic, we are going to actually record the time history with the Observer 1000 as a raw time history, and then we will post-process it in the transient capture software after we've done the acquisition. This is one to be able to demonstrate some of the features of the Observer 1000, the autonomous triggering and live analyzer that we expect to release here in the next 4 or 5 weeks, so around June 1, 2020. And to demonstrate that you don't necessarily have to use some specialized Vibration Research hardware. Any data acquisition system that can export to CSV, WAV, text, RPC, any of those generic file formats could be used, and the same process could be applied to generate that appropriate test. So we'll be taking the long road today. So what we're going to do, I have my accelerometer set up here. I'm going to set up some triggers on the Observer 1000, and we're going to record that data. Once I have the data recorded, I'm probably going to cut and crop that raw waveform to get rid of some of the dead space before and after, so that we don't have an incredibly long duration pulse where the majority of the demand signal is at zero. I want to just import the pulse that I'm looking at. We could do some basic analysis in ObserView, and then we'll move into Vibration View, where we will actually create a transient capture profile and graph layout that we can then apply to all of those recorded time histories, have that analysis done. From there, we will look at the SRS acceleration plots, copy and paste that data out to make a enveloped profile in Excel, and then in the end, go back and build a SRS test that has that enveloped SRS profile as the demand, and we will synthesize from user waveform using one of our recorded events. So with that, let's get started. The first thing that I'm going to do is set up my recorder in ObserView. So I can connect to a device, discover my devices, and in this case I have an Observer 1000 that is connected to my PC via Ethernet. And that Connect to Live Analyzer button that I just clicked is a feature that will be released in the next release, 2020.2 of ObserView. So here I have this live time data signal coming in. I need to set up my inputs. In this case, we'll turn them all off. And I have 2, 3, 4, 5, 6, and 7 connected. Turn on the accelerometer power for each of those. And we'll just hit delete to get rid of all those transitions. So now if I do something as simple as pull the trigger on my drill, I can see that vibration, and I can see that I'm getting pretty close to the signal that I would expect. Alright, so I have my input set up properly. The next thing that I'm going to do is look at my trigger. In this case, I do have it set up, but we'll just delete it and reconfigure that. So I'm going to do a new trigger, and my event is going to be if any of my channels that I have activated, 2, 3, 4, 5, 6, and 7, rise above, we'll just do 10 Gs since I'm getting, we'll make it a little bit less than that. Let's just do 5 Gs. So if any of those events, or if any of those channels rise above 5 Gs, I want to record for 3 seconds, but I want, we'll make this a little slower, 2.5 seconds, and I want 0.5 seconds of that to be pre-trigger. So we have a rolling buffer, and when I have a triggered event, it's going to start recording half a second before that event occurred and then give me 2.5 seconds after that event. So if I click save, I can then go and look at, let's do settings. I have to enable my trigger. Yep, settings. So I can do sample rate. We'll just crank this up to 81,920. So we have a nice round number. I'm going to call this impact drill. So click apply there and get my sample rate changed. I can change my time. I can format the card. That all looks pretty good. And now the last thing we want to look at is our files. I do have a bunch of files from my tests on here, so what I'm going to do is go back to my settings, and I'm actually going to format that card a minute so that we don't have any old data left on it. Alright, so our SD card is formatted. We've got all our data gone. Here I'm going to only display the channels that I have connected. And now we are ready to do our acquisition. So I'm going to go to the trigger tab just so that you can see what happens But the key also is to look at this record box in the lower left-hand corner. So if I pull my trigger, I exceed that 5G limit, and now I have a recording that was created 2.5 seconds long. We'll do a couple more. All right, and then I have 4 screws here that I'm actually going to drive just so that we have another environment to look at. Wait for my recording. Once my recording stops, I am moving on to the next screw. And the last one. All right, so there I have done my recordings. Now I can do a couple of different things. I'm just going to turn this off, and we will open those recordings and do some basic analysis in ObserView. So I'm going to go to Files, and you can see all of them here. So I'm just going to download. If I just click on it, it will download them for me. So I just have 5 of them here. And I'm going to do open, 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 open. So now ObserView instances are going to be opened for all 5 of those. And I can close this live analyzer one. So as these open, it's going to open that recording. Process the data and display it here. So there I have 1, 2, 3. You can see those chatter events and the much higher acceleration. 4 and 5. So the first thing that I'm going to do is actually crop these just so that they're a little bit shorter, and I can do that by pressing the I key on my keyboard and the O key. It's going to highlight that area. I can then hit crop, and there I have one of them. I can do save waveform as, and we will just save it. Do the same thing for this next one here. This one's much lower in amplitude. So again, I'm just going to do I and O, crop. You can see that I only have peaks out up above like 20 Gs in this case. Click Save and Export. Look at the next one. Here's one with these chatter events from the impact of the drill happening. We'll crop, save, export. I'm just doing this to clean up some of that dead space, I guess, and we'll do it even more once we get into vibration view. We'll use the transient capture software to even closer find our appropriate peaks and other things that I could do if I wanted to analyze. I could look at some different graphs. So if I do add graph, I can look at a simple FFT. And if I decrease my lines here and change my, so this little time window is what is being included in my FFT. If I move that back and forth, you can see maybe some of the peaks associated with one of these really high chatter events. I can see that bounce. The other thing that might be worth looking at just for information would be a spectrogram. And I might need to go out to 2000 hertz. So here I can see some of that spectrogram content. If I change my minimum to like 0.1, get rid of some of this lower amplitude content here. There we go. And you can kind of see this dominant section in time. It's just interesting to see and how those frequencies look. Maybe in log it might be a little clearer. Yeah, so I got a lot of content below 500 hertz, and then in the higher frequency ranges it starts to pick up a bit again. If we go to So not a lot of useful content doing FFTs or anything like that. But this is just one analysis. We'll look at something more appropriate in Vibration View. So next I'm going to open the Vibration View software. And we'll open Vibration View 2019. Here we're going to start doing our actual analysis. So the first thing that I want to do once I'm connected to my hardware is actually build a template test profile that I'm going to use to evaluate all of these different recordings that I took. And the reason that I want to pre-configure that is that it allows me to set everything up and then use the exact same parameters time after time, rather than having to go through and manipulate all of those settings for each individual recording. This just guarantees that I use the same analysis parameters for each environment and for each recording. So the first thing I'm going to do is create a new test, transient capture. And we're going to trigger on 2, 3, 4, 5, 6, 7, because those were the channels that we used. We'll do 5Gs. We want to look at roughly 2500 milliseconds, and we'll put 500 of that as pre-trigger. If it's available, it will display. We'll analyze to a little bit higher frequency. We'll go to 10 kilohertz. Just so that we can analyze that far out. Next, I'm going to look at my SRS tab. This is where I set my SRS analysis parameters. So again, I'm going to change this to 10,000. I could change my damping and Q. I could change my SRS resolution. It's up to you and depends on the analysis that you're doing and the product that you're testing. So I'm going to click OK, and it's going to let me save that. So we'll call this Impact Drill Template Video, just so that we know that I'm creating something new. Now, I don't really care about this anymore. So I'm just going to close this, and we are going to open one of our waveforms. And I can do that in the Recorder tab. Click Open Waveform. And I have to navigate to where my recordings are, which is ObserView, Downloads. So Documents, ObserView, Downloads. Let's go to Documents, ObserView, Downloads. And if we open this up, we can look at, here are the ones that I created, right? 1, 1, 1, 1, 1. Those are the edited files. So I'm just going to open the first one. And we will set this up and then apply these same settings to the others. So once I have a waveform opened, I need to right click in the time waveform at the bottom, and I can do attach test profile. Attach test profile is going to let me select that template that I created. And it is going to apply those settings as soon as I hit the next button. So now it's done that analysis, and here this particular waveform is really only 1,000 milliseconds long. So I could modify my analysis if I wanted to. If I click edit test, I might make this only 15, well, let's just make it a little bit longer, 1,600 milliseconds. If I click OK, I could modify that. Oh, it's not going to do it because I've already analyzed. I would have to do right click, analyze, transient capture, 2, 3, 4, 5, 6, 7. Now I could do 1,600. Well, actually it told me like 1,750. And then click OK. Oop. There we go. Now click OK. And then click next. And it's going to reprocess that for me. Could do that. It's not exceptionally necessary. Now the key is I have this transient capture profile, and I now want to, so we'll do this again just to get back to the same thing that we had before. And I want to create some graphs. So we're going to do edit graph. This first one, we'll look at channel 2, acceleration, velocity, and displacement. So I can see all of that. Here's my acceleration, velocity, and displacement graphs. If I create another new graph, I can do channel 3. Click OK. Now if I hit edit graph, I can actually just click new, and it would make it for 4. If I wanted to, I continue to insert these graphs, and it would give me 5, 6, and 7. We'll just do these 3 channels for the sake of it. And I'm going to create one more series of graphs. In this series, I want to view the SRS acceleration for channels 2, 3, and 4. So now, if I hit tile vertical, I have my acceleration, velocity, and displacement for channels 2, 3, and 4. And then I also have the SRS plot for channels 2, 3, and 4. And what I'm going to do, just to make all of this even easier yet, or more repeatable, is I'm going to go to Graph. I'm going to save this graph layout, and I'm just going to resave over top of that file. And it's called Drill TCAP Graphs. And this is going to allow us to automatically generate these graphs rather than having to do it every single time we redo this analysis. So that was our first event. Now I'm going to go to Recorder, Open Waveform. Our recent folder was here. And if I scroll down, I did this first one. I'm going to do a second one. And I'm going to repeat this process, but now I've basically automated it all. So if I right click, I can do attach test profile and pick my profile. Once it's there, I can click this next button, and the software is going to analyze it. Then I can go to Graph, Restore Graph Layout, and Drill TCAP Graphs. And now the software is plotting all of that for me. If I click Auto Scale, auto scale all of these. And there we have that analysis completed. Let's just do one more. So again, recorder, open waveform, go to my folder where those recordings are. I did the first two, we'll just pick the third one, open that. Then I'm going to right click, attach test profile, my template, click next so that I'm at my first point. Graph, restore graph layout, drill TCAP graphs, and now I have all of this one done as well. So there is our basic analysis. I have all of those done. If I wanted to, I could click Save Data. Let's just do that a minute. So we're just going to save the data for each one of these. So now I create a data file for each one, and it saves this analysis that I did. If I wanted to, I could then close all of these, open my data files that you can see here. Let's just do date modified by today, which is these three. Click open. And now it's going to open the static data file for each one of those transient captures that were done. Now, if I had done this in a VR95, using a VR9500 or Observer 1000 connected directly to Vibration View, I could have reached this point automatically just by my acquisitions. The software can be programmed to trigger. Once that trigger happens, this analysis is done, and it just gets me to this point right away. So that's why I wanted to show this. Interestingly, what I could do if I look at just this SRS, I can go to Edit and paste from files. So this is 1533-01. So I can copy these next two and click open. And now it has pasted, if I make this a little bigger so everyone can see it, I've taken all of my data from all my analyzed files and pasted them all onto the same graph, so I can compare all of those. And you can see some are high on the low frequencies, some are higher in the high frequencies. What I'm going to do is copy this graph and then open Excel. Create a blank workbook, and we will just paste that data. So that is, the pasted traces won't copy over, but that is my first one. If I open this one, that's the one I already have open, so let's just move this back into here. So that's the first one. We'll copy this one. I'm just going to click in the graph, hit Control-C on my keyboard, and then go back to Excel, hit paste. This is our next one. So those are our three environments. If I insert a row above that, I could do let's just merge and center. And then if we copy this over here, recording 2, recording 3. All right, because I used the same parameters, my SRS frequencies, the breakpoint frequencies, are the exact same. So what I'm actually going to do is just delete the frequency column for 2 and 3. And then I'm going to insert a new row or a new column here. And this is going to be our max G. So we're just going to create an envelope of all of the measurements that were taken for each frequency point. And I can do that by equals max of this series. Then I can double click on it and it will copy and paste that all the way down to the bottom. So now I have this envelope of all of my recordings. In this case, it's just a couple of drills, but I could repeat this process over and over and drive different length screws or have different configurations, different uses. Let's say I was doing a battery test. That same battery could be used in a Sawzall or a air nailer, or excuse me, a battery powered nail gun, a Sawzall, a circular saw, a grinder. I have all kinds of tools that I could compare and see how that battery is affected in different ways. And I could use this to create those transient events and envelope them all together into one super envelope that encompasses the worst case scenario that that drill or that battery would see throughout its testing. So now I'm just going to highlight all right, I have something weird going on here. So none of that matters. There we go. So I'm just going to highlight this row of data. I have 83 breakpoints. I'm just going to copy that. And we're going to go back to our live instance of ObserView, or of VibrationView, excuse me. So I can create a new test, and now we're actually going to create the test profile. And the first thing that I'm going to do is paste in my breakpoint table. So I copied that from Excel, and now I'm going to paste that in. Here I have a breakpoint table that goes from 1 all the way to 10 kilohertz. Most likely my shaker isn't going to have that frequency range, so we're going to test from, let's just do 10, kind of where this upward slope is, to, let's just do 2 kilohertz or 2500, somewhere in there, wherever I have a breakpoint. So I'm just going to scroll down. Here I've reached, that's my 10 hertz point. So I'm going to make that my first point. So if I click out of that, there, now 10 hertz is my first point. If I scroll down here, we'll go to 2048 is a good number. And we'll make that my last point. All right. So there I have from 10 hertz to 2048 hertz. And we're going to change our tolerance. We'll just do like minus 10% just to give us a little bit of wiggle room here, so that when we control, well, we'll just do 20 so that we can make it even easier. We need to have our either synthesize our SRS environment to exceed the demand line, or our tolerance needs to be less than the demand line to allow that test to actually operate. Next, we'll go to the SRS tab. So here I have my SRS analysis frequency range. I'm actually just going to leave that for 1 to 10,000 so that I can compare it to the same analysis that I did in VibrationView on the data files. Now this is where we would select our synthesis type. And here I have all of these different types of environments. If I look at damped sine waves, you can see that I can synthesize and iterate this. It fairly closely matches my demand. And if I look at my time history, it is essentially this series of damped sine waves that progress all the way out across 1,000 millisecond pulse. If I did wave sign centered, you could see, again, if I go to SRS, I can iterate this. I can get it to fall within my tolerances. It would take some manipulation to get some of this lower frequency content to be sharper. If I increased my resolution, I could get it better. But you could see that it's a completely different time waveform, and it has a somewhat similar shape to a terminal peak, where I have this kind of sharp transition up. This one has some negative energy as well. The last one we'll look at is like a burst random. So again, if I synthesize this and iterate, you can see that I can get it to closely match here. But when I look in the acceleration, this really looks nothing like the time history file that I saw in ObserView, like this, with these chatters and big spikes. So it's how similar are those two tests is the real question that you end up running. So if I look at my spectrum, we can modify that spectrum to get it to look fairly close. But I want my time duration and the overall pulse shape to be very similar to what I ran. So that's where Vibration View has this additional option called From User Waveform. And what we can do is import a user waveform. If I click Browse, go to Recent Locations. We just got to navigate there. So it was under Documents, ObserView, Downloads, and I have to change my file type from any of these generic file types to Recorder. And now I can use one of my edited waveforms. So we'll just pick this one. I can pick the column that I want to import. So if I had a particular channel, 2, 3, or 4, I could do column 1 is going to be channel 2, column 3 is going to be 2, 3. So we'll just do column. I can just scan it. So that had 5.2 G peaks. Column 1 had 8 point something. Column 3. Sure, we'll use column 3. It's kind of in the middle. So we'll use column 3, and I'm going to import that file. Now, when I look at this, the acceleration has a similar shape. So this one is actually, this recording does not have those chatter events in it. So this must be just the drill running. Let's look for one that has the chatter events so we can see the difference. We'll pick this third one and import the file. And now if I look at my acceleration there, I can see, but I have all this junk at the beginning. We're gonna have to change. There we go. If I hit synthesize, I can iterate that. Now I have something. Let's do this one more time just so that everybody can see what happens. There's my pulse. I'm going to import that. And you can see what that SRS is. That's my SRS for the imported waveform of the channel that I imported. Now, as I hit synthesize, what's going to happen is I'm going to pull and tug on the peaks and the frequencies of this waveform ever so slightly. If I click that a few times, you can see that it changed. I got a little bit more peak acceleration here. And if I look at my SRS acceleration, this now very closely matches what I am looking for. I can continue to iterate that to make it closer and closer. The next tab is the Wavelets tab, and one thing that is unique in Vibration View is that wavelet manipulation is automated. If your part has a resonance or if your shaker has a resonance, Vibration View is going to, in between pulses, manipulate this wavelet table in order to work out how to control the demand or how to get the control to closely match the demand. And it does that by manipulating this wavelet table and actually adjusting that in between pulses to get a better test. So now, if I wanted to run this, let's save this. I'm going to bump up my integration filter to minimize my displacement. That is just calculated. It's not actually changing the displacement of the test. It's just minimizing what is going to be included in the calculation. Then I can hit start, and I might have to, let's just change this right off the bat. On my limits tab, I'm going to need to increase my max output voltage limits. So now if I hit start, we can see this test fire up. And we'll create a new graph and look at SRS acceleration. Hit tile vertical. And now I'm running my pulse, and you can see that my SRS response is within tolerance. So if we do click on this graph and do edit, paste from files, let's just pick our few data files here. We'll just copy the data out of this one. Let's look at one of these. So if I copy this and paste that, you can kind of see that those time traces are very similar to each other, and that I'm getting very similar SRS and energy spectral density, which is the last comparison that I want to do. So we look at this energy spectral density. What I'm going to do is copy that and go back to one of my data files, this one that I had pulled out. So we'll make that bigger. If I edit this graph and insert a new one, do that, we'll look at all of those. So there, and now if I paste in my new graph, you can see that in that frequency range, I very closely follow the exact same energy spectral density as I did before. The last analysis that you could do if you were really interested would be a waterfall plot and compare if you had the IEEE 344 package. There is an additional graph called waterfall where you could plot how that energy is distributed across the time duration of the pulse and compare that as well. So that is the trick to generating complex shock pulses based on real-world data. And in the end, it's better in that you are using a time waveform that is representative of the real-world environment that your product is going to be exposed to as the baseline for the test that you're running. And you can use that to encompass multiple environments. All right, those are my conclusions. If you have any questions, please feel free to email them to vrsales@vibrationresearch.com and or give us a call at 616-669-3028. Thank you for your time.